So previously we defined the derivative as the gradient of a function at every point of x. So we talked about how the derivative of a function y as a function of x is equal to the limit as delta x goes to 0 of the following function. So f of x plus delta x minus f of x, and here we have delta x. So y is the function of x, so we just represent it as this. So now what's the deal with this? Well, let's say that we want to find the gradient or the derivative of the function x squared, which is just a parabola. So that's going to be our function x. So let's find the derivative of that. Well, let's see. First of all, we know what this is, so we can plug it into the formula. But what is f of x plus delta x? Well, it is going to be, because this is defined as that, what we're going to do is we're going to replace this x by this term, which is x plus delta x. So we're going to put it in here. And we now need to expand it out. So what's that going to give us? X squared plus 2x delta x plus delta x squared. So that's what we're going to get. And now if we plug it into the equation, that means that our dy dx is going to be the following. So limit as delta x goes to 0 of the function x squared plus 2x delta x plus delta x to the power of 2 minus x squared, because that's what f of x is. And all of this is going to be divided by delta x. So immediately we see that these two terms are going to cancel out. And then we're going to be left with these two. So we're going to have the limit of delta x going to 0. So obviously this and that are going to cancel out. And then this one is going to be left with the following. So 2x plus delta x. And because delta x goes to 0, this is just going to be 0. So in the end, we're going to end up with 2x. So what this is telling us is that the gradient at any point on this function x squared is going to be equal to 2x. So that's going to give us the gradient of the tangent line at each point, and that's going to tell us how fast the function is increasing. So what we can notice is that as we increase the values of x, you can see here that this function is going to be increasing more rapidly. And that change is reflected by this derivative. So basically what that's going to do to our function is, well, that's going to give us a set of points, or simply a value of the gradient for each individual point that we choose. So that's what the derivative is all about. Now, obviously, there are a lot of methods that have been developed for finding derivatives that don't involve these long calculations, because what happens when you have to derive something like x to the power of 20? Obviously, you wouldn't want to expand a polynomial of order 20 here and then like cancel terms out. That's very inefficient, and we don't need to do that. There's another thing called the chain rule, which tells us that for any function x to the power of n, and here I am using d over dx as an operator. So an operator is a mathematical entity that takes on a function and then performs a certain operation on it. So in this case, what this is doing, it is taking the derivative of this function as a with respect to x. So the derivative of this is going to be equal to n times x to the power of n minus 1. And we can check to see if this is true with this example that we just did. So what's the derivative of x squared according to this formula? Well, n is 2, so that means we're going to have 2x here at the front, and then at the power we're going to have 2 minus 1, and this just becomes 1. So yes, that is 2x, and that gives us the same answer that we got here using the derivation from first principles. And there are a whole bunch of other properties and really important formulas. So for example, this operator is linear, which means that for any number of functions you can have a is a constant times some function of x plus b another constant times some function of g, so function g of x is going to be equal to a times d of f of x over dx plus b of the derivative of the function g of x with respect to x. And there's another shorthand notation that we can use. So d f of x is over dx is going to be equal to f prime or f dash of x. So this is another notation that we use, and it's shorthand, so it's a lot easier to write than this one. So this is often used in long derivations. And along with these three properties, there are a whole bunch of other things that are standard results, and we don't really need to know how to derive them, because in the end what we're interested in here is with how do we apply this to solving problems and to finding the derivatives of functions. So just to give you some of the most common and most important derivations and derivatives. So let's say we have the function sine of x, then this is actually given by cosine of x, and the derivative of cosine of x is given by minus sine of x. And this is quite an interesting thing, because it means that if you keep taking the derivative of this, they go back to the other function, but the signs keep changing every time. So it's kind of a cyclic, it's an endless cycle of derivatives. So it's a very interesting connection between sine and cosine. We also have the derivative of the following, so that would be e to the power of ax. So e is just the exponential function. It is just a times e to the a times x. So one interesting property of the exponential function is that when you differentiate it, it actually doesn't change at all. The only thing that changes is that you now multiply by the constant that is in front of the x here. In fact, you actually multiply by the derivative of the top here. And we're going to do some examples of that in future videos. And then finally, what happens when you have a logarithmic function? Well, say you have the natural log of some function of x, and then we want to find what the derivative of this is. Well, it's going to be the derivative of the function over the function itself. So that's another interesting property. And these are some of the common derivatives that you can find, but there are a whole bunch more, and you can find them in tables, you can find them online. Pretty much everywhere you look, you're gonna find massive list of derivatives, and that's usually what we use to solve problems, because it's a lot quicker, and the essential idea is that we want to derive a function that will represent the gradient of a specific function as it changes with the different values of the independent variable. And in the next video, I'm going to show you a very important technique for differentiation called the chain rule, which is where we get these derivations from.